All right, we're looking at these, I'm going to call them curve sketching problems for lack of a better word. This is number 39 from 4.3. In fact, here it is in the book. So if you look at the instructions here, zoom in a little. It says we're going to find the intervals of increase and decrease. We're going to find the local maximum and minimums, the intervals of concavity and inflection points, and then we're going to sketch a graph. I'll talk about a few more things than just that in order to sketch a good graph, but those are what we're looking at. And then the next problem we look at, I think, is from this part, or I don't know if I took it from here or that one, but find the vertical and horizontal asymptotes, intervals of increase and decrease, maximums and minimums, concavity, inflection points, sketch the graph. So we're just doing a deep level analysis of these functions using everything you knew from pre-calc, but also from calculus now. And it's actually easier now because when you did this stuff in pre-calc, you didn't have as much to go off of. But now with the tools of calculus, you can know a lot more about these functions and what they do. So the first thing I would do on any of these, with the book questions, follow the instructions that they give you and give the things they ask for. You don't have to do more than that. But we're kind of leading into stuff where I'm just going to ask you to kind of do everything. So I'm just going to look at it that way. So I'm going to start by thinking about the domain of this function. And the only domain restriction that we have on f here is from the square root. It is an even indexed root, which means the inside of it must be non-negative, greater than or equal to 0, right? Otherwise, we'll have imaginary numbers. So I'm thinking, 6 minus x is greater than or equal to 0. You might be able to just tell, hey, x is going to be less than or equal to 6, including negative values, by the way. But you can also just solve this inequality if you write it out by adding x to each side. And so my domain is negative infinity to 6, with a bracket at 6, including the 6, right? While I'm at it, while I'm talking about f, before we get into a derivative, you can also find zeros of this function, which if I'm going to sketch a graph would be helpful. There's one at 0, 0, and there's one at 6, 0. So 0, 0 is the origin. 6, 0 is that right end point of the function. That's kind of like one of the end behaviors there. While I'm talking about it, end behavior is another thing to consider. So I already know the right end, right? This end of the domain, which is that it has a 0 there. There's a point there. We'll figure out how else it kind of goes into that point in a minute. On the left end, I could do a limit as x approaches negative infinity. Limit as x approaches negative. And again, this wasn't requested by the problem, but doing it tells you what the graph's going to do over there. As I do that, I'm looking at a negative infinity times, this becomes like positive infinity, square root of positive infinity. So we're looking basically at negative infinity times positive infinity. The magnitudes just get bigger. Negative times a positive gives you a negative. And so this function is going to go down to the left. That's what that tells me. I will get evidence to back that up from my first and second derivative analysis too, though. So I don't necessarily need to have done what I just did there. I'm going to kind of put this, we'll put it here. All right. Now, first derivative. And if you want to pause and do the first derivative yourself first, that's a good idea. There's a product rule here, right? In fact, it might be helpful to rewrite the function up here. Let's see, I was doing f in purple. So x times 6 minus x to the 1/2, right? That's how we do this derivative. Okay. So I'm going to do a product rule. U prime, that's my u, right? It's just going to be 1. 6 minus x to the 1/2 plus u, which is just x, and then my v prime, which is going to be 1/2 times 6 minus x to the negative 1/2 times the derivative of the inside there, which is negative 1. Okay. And so I have a negative 1/2 x if I put this out here. I'm going to go ahead and factor this. I'm going to shrink it up a little first here. And what I like to do is I'll factor out the 6 minus x to the negative 1/2 power. You can also turn this into a denominator, a square root in the denominator, and then give this term a common denominator and put them together, right? If you prefer. So I'm going to factor out 6 minus, this is the same, it's the same algebraically. I'm factoring out 6 minus x to the negative 1/2, and from the first term, that leaves 6 minus x to the 1, right? And if you're not sure what I'm saying there, let me just point out, if you take this and you distribute it to this, because we're going to have plus some other stuff in a minute, you would add the exponents. Negative 1/2 plus 1 is positive 1/2, and it gives you that term. So that's what I've represented so far. When you factor something out, you divide. And so I'm factoring this out, which means I take this divided by this. And when you divide, you add you subtract exponents. So 1/2 minus negative 1/2 gives me 1. That's another way to think about it. Okay. So that's from the first term. Then I need to do the second term. And what I factored out was 6 minus x to the negative 1/2, which is this whole thing. And what's left is going to be negative 1/2 x. Now, if I wanted to, I could have also factored out a 1/2 while I'm at it. And I don't know, maybe that makes it more complicated. So we'll keep it like this. So minus 1/2 x. Okay, and then that's obviously a 3/2 x when you combine those. So let's rewrite it one more time. 6 minus x to the negative 1/2, which of course you can write as a square root on the bottom of the fraction. And then this is 6 minus 3/2 x. That last form is where what I'm going to use for my sign chart. As for doing another derivative, I could do it from here. Whoops, that's not what I intended to do. Different problem I was working on for a different class. I could do that form for the derivative and do a product rule, or I could clean this up a little and do a derivative from this form. However, I'd still have a product rule here. I'd have a x times a stuff here. So I think I might just go from that last form for my second derivative. And you know what? I'm just going to go ahead and do it right now while I'm talking about it. I'm going to do it anyway. Prime of x equals, and again, I'm looking at u times v. So u prime is negative 1/2. 6 minus x to the negative 3/2 times a negative 1 for the chain rule. So I'll just make that positive. Times my v, 6 minus 3/2 x. Plus u, 6 minus x to the negative 1/2 power, times v prime, which is negative 3/2. Okay. And now I'm going to factor out again 6 minus x to the lesser of these powers, which is the negative 3/2 power. While I'm at it, I'm going to go ahead and factor out a 1/2 as well, since they both have it. It makes it kind of easy to do. So let's rewrite this. Equals, and this term is negative. I'm just going to kind of keep an eye on that. I'm going to have a negative in front. This one's positive though, so I won't factor out a negative or anything. I'm going to factor out 1/2 6 minus x to the negative 3/2 power. And that's going to leave, well, that's all of this. So it's going to leave 6 minus 3/2 x. And then from the other term, we took out the 1/2, right? So it's going to leave this negative 3 from there. And then it's also going to leave us 6 minus x to the 1 power because this is 1 more than that. So it's going to be minus 3 times 6 minus x. That's what's left there. That 3, the negative with it, and one of these. All right. Then I'm going to clean that up. First, I'm going to shrink it so it fits better. And When I say clean it up, I mean specifically the inside here. So that's minus 18 and then plus 3x. And when I put it together with this stuff, that's going to be positive 3 halves x minus 12. So that's that last factor. And then with this stuff as well. And again, there are things we could have done differently. We could have factored out another 1/2 to get rid of all the fractions in these factors. And then this would be like a 1/4. It doesn't matter. It's however you do it with that stuff, as long as you're consistent, it should work out in the end. You should get the same kind of results. All right. Whoops, I kind of screwed up that x. Just wanted to get this part. Whatever. So, sign charts on F prime. Key numbers. We got 6. Well, that's an endpoint already of the domain. I'm only going from 0 to 6, right? I'm only looking, negative infinity to 6. I'm only looking at any of these functions on the domain of F. So I don't have to worry about that one. And then this one, that's where the real critical value is going to come from. So I'm going to set that equal to 0. So 6 minus 3 halves x equals 0. 6 equals 3 halves x. Multiply both sides by the reciprocal, and you get x equals 2/3 of 6, which is 4, right? That's our key number. And so for my sign chart on F prime, we're going to go from negative infinity up to 6, and we're going to put 4 on there in the middle, and we're going to go ahead and, thank you. Appreciate it. We're going to go ahead and do the sign chart on those two intervals. So when you look at from negative infinity to 4, you can look at you could list these factors separately if you like. It's probably a good idea. Actually, I'll go ahead and do it that way since they're kind of funky factors. So if I put the, this is a negative 1/2 power. That's a square root in the denominator, right? So 6 minus x to the negative 1/2. That negative 1/2 power, though, it doesn't change the sign of anything, right? So when I plug anything in this domain into here, this is going to be positive to a negative 1/2 power. It's still positive. So this factor is positive over the entire domain. And then the 6 minus 3 halves x, that factor is a linear factor with a negative slope, which means it's actually going to go from, if you graph that line, it would look like that, right? It's got a negative slope. It's going to go from positive values to negative values. And the reason I say that, you can test points, but you can also just realize it's going to go positive to negative. If you test points, what I mean is plug in 0 maybe over here, since 0 is left of 4. If you plug in 0, you get a positive value, you get 6. And then when you cross 4, sure enough, this will become negative. If you put 5 in there, whatever, it's going to be negative. And so the whole thing, F prime, is positive and then negative, because a positive times a negative is a negative. All right, what does that mean? That means that F is increasing on the interval from negative infinity to 4. Okay, and I will include 4 in that. 4 is a place where F prime equals 0, right? It was a 0 of F prime. In fact, I could label that right here. F prime equals 0, right, at x equals 4. And so what that means is that's a horizontal tangent, and that's going to be a relative maximum. And then F is decreasing from 4 up to 6. And if I plug 6 into the derivative, I actually get a 0 denominator. I'm going to go ahead and include the 6, though, because it is in a domain, and we are increasing up to and including that point. I'm sorry, decreasing, right? I'll show you what that looks like in a minute. The fact that it's a 0 denominator, if you just think about it, that's the slope of the tangent line to the curve at that end point from the one side, from the left side. When do you get an undefined slope? It's when a line is vertical, right? So that just means we're going to be coming in vertically to this right endpoint of the function, we're going to be curving in toward a vertical tangent. That's all. That's what it's going to do at the end, which, it's got a square root piece in it. That's kind of what square root functions do, right? All right. This means f has a relative max at x equals 4. I'm gonna give the coordinates though. 4 comma, and we need to find it, right? So f of 4 is 4 times 6 minus 4 is 2, so 2 to the 1/2 power. 4 square roots of 2. Okay, and so that's our kind of details there. Just going to shrink this up a little bit so it fits a little better in there. Maybe this stuff too, if I can. I don't know if it's going to let me. I can fix that circle. That's no problem. This is where f prime equals 0, right? So, all right. So far, so good. Same thing on f double prime. It's taken a while, but I'm talking through things in a lot of detail as well. You can use sign chart on these factors. You can ignore the 1/2. It's positive. It's not going to affect the sign of anything. And so, yeah, if you kind of list out, again, we're going up to 6 and off toward negative infinity. Again, you can do the 6 minus x to the negative 3/2 power. This is going to be positive over the entire domain. The negative 3/2 power will not change that. So we're going to be positive all the way through there. And then the 3/2 x minus 12 is the other factor. So I need to get the 0 from that, right? That's going to be where f double prime equals 0. So 3/2 x minus 12 equals 0. 3/2 x equals 12. Multiply both sides by 2/3. X equals 8. Okay, now think about that for a second. X equals 8 is outside of the domain of the function. So the only place where this thing can possibly change signs, this value right here is outside of the domain, right? Because it would create a negative inside of a square root. And so that means this thing does not change signs. The second derivative does not change signs. That means we don't have any key numbers here. There's going to be one sign. It's either positive or it's negative. This factor is positive, we already said. And then this factor, well, this is a line with a positive slope, right? 3/2 is the slope. And if you picture a line, it has a 0 somewhere. That 0 is at 8. Well, we're talking up to 6. So to the left of 6, this thing is negative, right? And that's over the entire domain of the function. It would change negative to positive at 8 if I had 8 on my sign chart, but I don't. So, whoops, I was saying it's negative. And so the whole thing, f double prime, is negative. And so f double prime, I wrote lowercase f there. That's not quite right. So it's actually true that f double prime of x is less than 0 for all x in the domain of the function, right? Which is, there's that lowercase again, which is from negative infinity to 6. What does that mean? That means my function is concave down over the entire domain. And I could write that. F is concave down for the entire domain. There is no point of inflection on this graph. All right. With all that in mind, I think I'm ready to graph this thing. So, got a few key points here. I'm just going to go ahead and shrink everything up a tiny bit more so I have a little room to work with. Oh, it doesn't want me to. Okay. And I don't think I need a lot of room here. So again, we're only going up to 6. I'm going to go ahead and just kind of put 6 over here. And the point was 6, 0, and then 0, 0 were the zeros. And then we had another special point at 4, and 4 radical 2. Right, so there's 4. And I'll just put 4 radical 2 up here, 4 square roots of 2. Square root of 2 is about 1.414, so that's pretty close to 6, actually, a little less than 6. But who cares? It's, it's 4 square roots of 2. That's the value. So we're going to pass through that point as well. Again, I know the function is going down to the left. I know that the function has a relative max at this point right here. I know that the function is increasing up until 4 and then decreasing, right? And I know that it's concave down the entire way. So, and I also know that it has a vertical tangent at this coming into this right end point. So it's going to look something like this. It's going to pass down through here. And it's just going to go off forever to the left and down, right? It's pretty steep. Just keeps going. Concave down the whole way. Here, let me highlight a few things. It's concave down the whole way. It is increasing to there and then decreasing to there. It has that relative maximum. It has that vertical tangent. It has the zeros that we identified. And that's really it. That's all the details, right? But those details, I mean, there's so much in here, so much analysis that helps us to know what this function does. And that's really the point. It's not so much about being able to graph things by hand, although that's kind of cool. But it's about being able to look at these functions and being able to analyze them in any way that we need to say whatever we want to find out about them.